So we're going to continue on with the greenhouse effect. Where we left off is that we, at 0th order approximation of the Earth's equilibrium temperature, we came up with a temperature that's way too cold. And then we said, hey, the Earth doesn't radiate away energy at the rate that we expect because of the inhibiting effect of greenhouse gases. So there's two ways you can look at that effect. The approach that I took was just to say, because that absorbed infrared radiation is re-radiated back to the Earth, what really is absorbed at the ground level is this value here instead of the predicted 235 based on the solar constant and albedo. Another way you can look at it is we can keep this number as 235 and just adjust Stefan Boltzmann's equation and put in an emissivity of less than 1. So they both work out to the same value. So what we want to do in calculating that new equilibrium temperature is, again, when we reach equilibrium, our I in equals our I out. And so we're going to use for I in instead of the 235, we're going to use 390. That's the enhanced. Okay, that is an important word from the IB, enhanced version, because of the greenhouse effect, is now going to equal sigma. So and I'm sure you're going to be confused with this. Let me clarify. I took the epsilon out of that because, in essence, what I did is I brought it over here. So let me just do something to the side if you're confused, and perhaps I should have done this to begin with. If we've got I in equals epsilon sigma t to the 4th, I can bring the epsilon over there and say I in over emissivity equals sigma t to the 4th. And so since the emissivity of the Earth is less than 1, then this divided by that is going to give us a bigger number, and that's where the 390 comes from. Okay, so that aside, if we solve for temperature once again, and this is the equilibrium temperature, we get 288. And I suggest you work this out on your calculator, okay? Just don't take my word for it. And again, that's Kelvin. So to get that to Celsius, we get 15 degrees Celsius. And it works out very nicely. Okay, so what we're seeing is this is the natural temperature of the Earth. This is not the human-caused AGW. This is, at least since the last ice age, what the average temperature of the Earth has been. Obviously, there's variation with latitude and variability from certain phenomena like El Niños, La Niñas, etc., volcanism. But we see that without greenhouse gases, water vapor, carbon dioxide, methane, okay, we would not have the planet that we have civilization has developed. Okay, very little life would have developed. So this is super important. So the greenhouse effect is huge. Okay, so this is called natural global warming. Okay, not to be confused with what we talked about before. Okay, and it leads to, and it has led to the greenhouse effect. I'm just trying to look at, and it's led, for about as long as we've had an atmosphere. Okay, the amounts of greenhouse gases has fluctuated for a variety of reasons. Okay, but without it, we're in trouble. Okay, so and I just want to make also clear, and I'm just double checking to see if I have this on there, is the AGW that we've talked about before is going above and beyond this, dumping in even more and more and more and more CO2. We have increased the concentration of CO2. We're also, I think we're close to doubling it from historical levels. So the temperature is going to increase. It's not going to double. It's a logarithmic effect, and it is going to reach equilibrium. It's not a runaway effect like Venus. If someone's trying to convince you that greenhouse effect is not occurring on Earth, it's not an issue, just point them to the planet Venus and have them explain why it's the hottest planet in the solar system. Okay, it's a runaway greenhouse effect. We're not necessarily going to have that, but we already know that any slight warming is going to be potentially catastrophic. Okay, so why, let's remind ourselves, why do greenhouse gases absorb infrared radiation? Because we know that the molecules vibrate, okay, at the same frequency as infrared. There's an overlap, okay? In other words, it's a resonance effect. So IB, you might be asked to explain that qualitatively and go into some detail without necessarily having to do the numbers. Okay, so now let's get to the AGW, anthropogenic global warming. So as we've already learned, it is occurring because we're dumping a ton of CO2 in the atmosphere for quite a long time, thus affecting the output, okay, of the Earth's radiation. All right? So simplistically, we now have I in is greater than I out. We're not getting rid of radiation as efficiently because of that blanket effect. And this will cause the temperature to rise until thermal equilibrium is once reached again. So a fairly simple equation, it's a little simplistic, but it gives us a ballpark idea of what to expect, is we can predict the change in temperature based on this imbalance and the amount of time that this imbalance remains. Okay, so the equation that predicts this is you just look at what I in minus I out, right? Simply the difference. And if it's a negative difference, that's going to be a cooling effect. Multiply whatever time period you're interested in, divided by, and I'm going to put a big CS here, where CS is like the surface heat capacity of the Earth. In other words, it's a number that takes into account the structure of the Earth, the material, the water, the land, etc., and assigns a value of a capacity, which is 4.0 times 10 to the 8th, okay, joules per kilogram per degree Celsius. Okay, so if we look at a simple situation, so suppose the input, because of the greenhouse effect, goes from the standard 390. So remember that 390 that we used in the previous one, that's natural. That's what we've had, let's say, for the last 10,000 years, through which civilization has developed. And let's say because of the AGW, the enhanced greenhouse effect, it jumps up to 2 watts per square meter. Remember that number that came up in the balance chart from the previous tutorial. So we could then ask, what would be the change in temperature, let's say, after 6 months of this? And 6 months is that amount of time. So I could say the change in temperature is the I in minus I out. So I'll just put 2 degrees or 2 Kelvin, or excuse me, 2 watts per square meter. Okay, multiply by that time, 6 months, and 6 months is not a lot of time at all. Okay, divided by that big heat capacity, or specific heat capacity, surface heat capacity. Okay, so plug in the numbers, and you don't get an impressive number. It's about 0.08 Kelvin or Celsius. Okay, but that's 6 months. For 1 year, that's 0.1 degree. And so you can see that this number is going to grow with time. Now, it's not going to grow at the same rate because the difference is going to start getting less and less. As the temperature goes up, the output's going to go up. So it's an exponential equation, but we can model this with a spreadsheet, and we'll do that as an activity next time. Okay, so if you have questions, ask. It's a little bit complicated, but it kind of makes sense. The big idea is that when the Earth, if you pretend the Earth started at 0 Kelvin, when you turn on the sun, it starts warming up. And if the input has stayed more or less constant, the output is going to grow with temperature until they reach a balance. And when you add in a greenhouse effect, that inhibits the outflux, so it's going to reach a higher equilibrium temperature than one would otherwise expect.